Hello, BC Calculus students. This is Mr. Johnson, and this is our first section, Chapter 4. This is Section 4.1 on related rates. And you have seen all of this from AB Calculus. In fact, a couple of these problems are similar or maybe even the same as what we did last year. So hopefully this section is a pretty quick one. There's some additional practice in our section here from AP multiple choice and free response exams. But I'm going to go through 4 problems with you pretty quickly with regard to the idea of related rates. Remember that when we're looking at related rates, we're looking at differentiating with respect to time. So when you have maybe a simple function like x squared and you're taking the derivative with respect to x, you simply get 2x. The variable matches the variable that you're taking the derivative with respect to. If you were to take, for instance, the derivative with respect to x of y squared, well, now you still get the behavior of the power function, so 2y, but then you're multiplying by the derivative of y with respect to x, simply because you're differentiating with respect to x, and you have y, which is not the variable of integration. If you were to take, for instance, the derivative with respect to y of x squared, you would get 2x. However, you would have the derivative of x with respect to y because now your variable of differentiation has changed and the x does not match that variable of differentiation. So you have this idea of an implicit derivative or a derivative where the variable that you're taking the derivative with respect to is not matching the variable that is written in the problem. So in related rates, what we're doing is we're taking the derivative with respect to time. So for instance, if we took the derivative with respect to time of x squared, we would simply get 2x, and then we would multiply that by dx dt, which is the rate that x changes based on time. So hope that makes sense. Just a quick overview of what we're doing with related rates. A little bit more practical problems, or problems at least that we can sort of picture or draw out, or a little bit more common sense with regard to what's happening. So in this first example, we have a small balloon that rises 150 feet from an observer, and we're assuming that that where the balloon is let go and where the observer is on level ground. We're also assuming the balloon goes up straight at a rate of 8 feet per second. So that's going to obviously be an important rate that we're going to talk about here. And we're looking for how fast the distance from the balloon to the observer is increasing when the balloon is 50 feet high. So let's fill in a couple more things here. We have this distance 150 feet. We also know that the moment that we're going to be looking at here is 50 feet. Obviously, that's only at one moment in time because the balloon is constantly changing. So the horizontal distance we have is 150 feet. We don't need a variable there simply because that is not changing. There is no change there. This horizontal distance, there's no change there. So therefore, we don't need to worry about any kind of rate of change since there is no change occurring. We do, however, have to worry about our vertical change. Let's just call that y, just to give it something easy to remember, because this is constantly changing. It starts at 0 and it increases. It does reach 50 feet at one moment in time, but then, just a split second after, it's beyond 50 feet. The other thing that's changing is the hypotenuse of this triangle, and let's go ahead and call that z just to give it a variable. We know the rate of 8 feet per second, which we're going to write as dy dt. The rate we're trying to find is the rate the hypotenuse changes, that distance. So we're trying to figure out dz dt. And the moment we're trying to analyze dz dt is when y is equal to 50. So we're able to sort of organize here what we're looking at in this particular problem. Now what we need to be able to do is come up with an equation that relates all of these variables together. And that equation will simply just be the Pythagorean theorem. We have a base of 150, we have a height of y, and we have a hypotenuse of z. So we can take 150 squared plus y squared, and that is equal to z squared. And again, y and z are changing, which means that we are unable to substitute any numeric values for them right now, because then that would take away from the fact that there is a rate associated with them. So our next step is to take the derivative with respect to time. Now, when we take the derivative of 150 squared, we get 0. Again, that should be obvious because there is no change that's occurring there. So the rate of change would be 0. Then we get 2y multiplied by dy dt and 2z multiplied by dz dt. So we have basically 4 variables here. We have y and z, and we have the rates of y and the rate of z. We could cancel the 2, just both sides of the equation, and then we need to start to substitute in our values. Now we're trying to solve for dz dt, so we're not going to be able to substitute anything for that, but we also need to figure out what z is, because we know y is 50, we know dy dt is 8, and then we're trying to figure out what in the world z is, and we have dz dt that we're trying to solve for. So we're going to find z by just taking the Pythagorean theorem. We know that the base is 150 squared, or 150, we're going to square that. We know that y is 50, so we're going to square that. And we know that it's all equal to z squared. And again, this is going to allow us to find what z is at the moment when y is 50. Without a calculator, there's actually a little trick that you may have seen before. You can separate this large squared number by taking 3 squared plus, or I'm sorry, 3 squared times 50 squared. And you're able to then factor out a 50 squared. This is a little trick that doesn't always work, but in this case it does. And so we're left with 50 squared times the quantity 3 squared plus 1 squared. So in other words, what we have is 50 squared times 10, 9 plus 1, and that's equal to z squared. So if we were to solve for z here, we would take the square root of 50 squared, which is of course 50, and the square root of 10, can't do much with that. And that's just a fast way of getting z in a pretty reduced form without a calculator. Anyway, it doesn't work for obviously every large number being squared, but sometimes it does. Okay, and then we're going to divide both sides. We are able here to cancel a 50, so we do get 8 divided by 10. We could rationalize the denominator, but I'm not going to worry about that right now. There's my rate. It does not ask for units, but just to make sure that we understand how to get the units, we're looking at feet per second here because we're looking at that rate, that distance changes based on time. And when I look at that, I always think of what are the units for z? Well, the units for z are feet. And what are the units for t? Well, time in this problem is written as seconds. And so therefore, I have this unit of feet per second using the derivative notation. Okay, let's try example 2. For this example, we need the volume of a cone, which is 1/3 pi r squared times h. And we're looking at water being poured in at a rate of 8 cubic feet per minute. The height is 12, the radius is 6. Let's go ahead and draw that in really quickly. So that's going to be 12, the radius is 6. And we want to look at how fast the water level is rising when the water is 4 feet deep. So again, we have a radius, we have a height, we have a volume. We know that the rate the volume changes based on time is 8. They give that to us in the problem. What do we want to know? Well, we want to know how fast the water level is rising. So we want to know dh dt. In other words, we want to know the rate of change of the height based on time. When do we want to know that? We want to know that when h is equal to 4, which is going to just happen in a 1 split second. Otherwise, it's constantly changing. So we have in our original equation for volume, we have 2 variables. We have r and we have h, and that's a little bit of a problem because we don't really know much about r in this problem except that at the top it's the opening is 6 feet. R, however, as we progress through the cone, R is changing in size. What that means is that we cannot put 6 in for R right now because R is only 6 at one moment. We also can't put anything in for H because H is constantly changing as well. And this presents a problem because if we were to take the derivative as it stands, we would have a product rule. And we also don't really know anything about R in this problem. We don't know how R changes. There's a little bit of an unknown there. So one of the tools that we can use is to just look at the relationship between H and R. We can see that at the opening, R is 6 and the entire cone is 12. And what that means is that if we use symmetry here to look at the cone, we know that, that R is half of what H is. So let me just write it like this, 2R equals H. And we want to make a substitution here for R in the problem. So we're going to solve for R. In other words, R is half of whatever H is. And we're going to use that in our equation. So we're going to take R and substitute in H divided by 2 and square that. And we get 1/3. Sorry, let's back up. We get 1/3 times 1/4, because remember we have H divided by 2 squared. So we have 1/3 times 1/4, which is 1/12, pi times H cubed. And this is what we're going to differentiate with respect to time. So when we take our derivative, we get dv dt, so we get the rate of change of the volume. We get the power rule, so 3 times 1/12, which is 1/4, pi times h squared, and then we have the derivative of h with respect to t. Okay, we know pretty much every variable except dh dt. So if we were to take dv dt and substitute in 8, we are then equal to 1/4 pi times h is 4 in this example, squared, times the unknown dh dt, the rate the height changes. And so if we were to just solve for dh dt here, by balancing the equation, we get 2 divided by pi. And in terms of units, remember h, when we think through the units, h is going to be feet, given the problem, and t is time, which in this problem is minutes. So our units here will be feet per minute. Okay, let's move on to example 3. All right, in example 3, we're going to look at a sphere. We're looking at a soap bubble. So assuming that the soap bubble retains its shape as it expands, how fast is the radius increasing when the radius is 2 inches if air is blown in at a rate of 4 cubic inches per second? We need the volume of the sphere, which is 4/3 pi r cubed. We know, based on the problem, that the rate that the volume is changing is 4 cubic inches per second. What do we want to know? What rate are we looking at? The problem says that we want to look at how fast the radius is increasing. So we're going to look at dr dt, so the rate the radius changes based on time. And then when that's going to occur is when r is equal to 2. So let's go ahead and start off with our formula for the volume, which is 4/3 pi r cubed. We're going to take the derivative with respect to time to get dv dt equal to 4 pi r squared times dr dt. And we're going to start to substitute in our values that we know. So the first one is the dv dt, the rate the volume changes based on time is 4. And then that's equal to 4 pi r, 4 pi, and then instead of r, we're going to substitute in 2 and square it. And then we have our unknown, the rate the radius changes. And so if we're able to balance this off and solve for dr dt, we end up getting 1 divided by 4 pi. And again, if we were to look at the units for the dr, the radius, is going to be inches. And then the time t would be in seconds. All right, let's try our last example. So we have a person standing on a cliff and they're watching a motorboat through a telescope as it approaches the shore directly below. If the telescope is 250 feet above the water level, so this length is 250, doesn't change, and the boat is approaching at 20 feet per second, at what rate is the angle of the telescope changing when the boat is 250 feet away from the shore? So let's just extend this ground here. you can see that the picture is not a real high quality picture. Okay, so we're looking at the angle of depression from the horizontal, which means that theta is the same here based on, I think in geometry it was the alternate interior angle theorem. Anyway, so this is the situation we have. Let's go ahead and give the horizontal x. We don't need to worry about the hypotenuse. That actually isn't going to impact the problem. And the vertical is always 250, which means we don't need a variable there either because it doesn't change. So we're trying to find the rate we're looking for is the rate that the angle changes, so d theta dt. We are given in the problem the rate that the boat is moving, which is dx dt. And this is a little bit tricky, and this is actually an error in our answer key. This rate is -20 because of the direction it's moving in. And then the last bit is when, and the answer there is when x is 250 feet from shore, okay? So the question is, what equation do we use here? Because we need to relate the angle with the vertical height of 250 and the horizontal height of x. And so we have a triangle here, and in problem 1 or example 1, we ended up using the Pythagorean theorem. But here we don't want to do that with side lengths because we don't really care about the hypotenuse. We only care about the adjacent and the opposite side of the angle. And if you think through the adjacent and the opposite side, you should at least start to think pretty quickly about the trig function tangent, and that's the equation that will relate all the variables together. Now we could certainly start taking derivatives right now, but what I would propose is that we solve for theta, because remember we're trying to identify d theta dt. So if we solve for theta now and then take the derivative, we might save ourselves a little bit of time. All right, the anti-derivative, hopefully you remember. So first off, we have d theta dt, that's what we're searching for. The antiderivative of inverse tangent is 1 divided by 1 plus the inside, so 250 over x squared. Then we have to multiply by the derivative of 250 over x. Now remember, 250 divided by x is the same thing as 250 x to the negative first. So your derivative is going to be the power rule, where you bring down the negative and decrease the power by 1. Now don't forget, really easy to forget, that you need the rate that x changes based on time, since that's the variable of the differentiation. Okay, we have a bunch of stuff here. We're going to go ahead and substitute in our value that we're looking at, which in this case is going to be x equal to 250. So what we get is 1 divided by, now again, if you're substituting in 250 here, you have 250 divided by 250, which is 1 squared is 1. So you end up getting, for our first fraction, you end up getting 1/2. So that's our first part. Then we have negative 250 divided by 250 squared. Well, that's going to simplify to just negative 1 over 250. And then our rate of change is negative 20. So let's go ahead and work on this for a minute. This is going to be negative 1 divided by 250. And we have negative 20. That gives us positive, of course. We have 10 divided by 250, which gives us 1 over 25. And again, that's going to be an error in the key in your workbook there. It says it's negative. It actually is positive. If you go back up to the original, that angle we're analyzing is getting larger as the boat approaches, and therefore it's going to be a positive rate of change. In terms of units, this is going to be the measurement we have for the angle, which is radians. And then in the problem, the rate of change is going to be feet per second, so we're looking at time being seconds. So this is the change of radians per second as we analyze this particular angle change. Okay, that's it from me for section 4.1. Thank you.